In this video, we analyze counter movement jump performance using force plates and high-speed video. A counter movement jump, or CMJ, is a vertical jump that begins with a rapid downward movement before takeoff. It is commonly used to assess lower limb explosive power, jump performance, and movement strategy. For this analysis, we use Vicon Nexus software. On the left, we see the video of the jump, with force signals overlaid on the image. When two force plates are used, we can look at the left and right sides separately to assess asymmetry. We can also view the combined signal, where the force from both force plates is added together. On the right, we see three synchronized graphs. The upper graph shows vertical ground reaction force, measured in newtons. This tells us how much force the person applies to the ground at each moment of the jump. The middle graph shows the estimated vertical position of the center of mass, measured in millimeters. This helps us see how the body moves downward and upward during the movement. The lowest graph shows the vertical velocity of the center of mass. This tells us when the body is moving upward or downward and how fast that movement is. All graphs are synchronized with the video. This means we can look at the movement, the force signal, and the center of mass movement at the same time. As with force plate analysis in general, the signal is much easier to understand when it is combined with video. At the beginning, the person stands still on the force plates. During this phase, the force signal should be stable. This part can be used to calculate body weight. In this example, the body weight is around 800 newtons. Notice that even hand movement can create small changes in the signal. During quiet standing, center of mass movement is minimal. In this example, the estimated center of mass is roughly around 1 meter above the ground. Next comes the unloading phase. This is where the counter movement begins. The person starts moving downward. As the body's center of mass accelerates downward, the contact force between the feet and the force plates becomes momentarily lighter. In the force signal, this appears as a clear drop in force. In this example, the force drops close to 100 newtons during unloading. From the video, we can also see that the right foot slides slightly forward during this phase. At first, the center of mass position has not changed very much. But the velocity graph already shows that the body is accelerating downward. When downward velocity reaches its peak, the braking phase begins. During the braking phase, the body is still moving downward, but that downward motion must now be slowed and stopped by active muscle work. The legs push against the ground, and the vertical force rises rapidly. This braking action prepares the body for upward acceleration. At the lowest point of the movement, the vertical velocity of the center of mass is momentarily zero. This is the transition point between moving downward and moving upward. In this example, the force peak at the bottom of the movement is around 2,300 newtons. The movement does not stop for long. The body quickly changes direction and begins to move upward. Now the propulsive phase begins. During propulsion, the body accelerates upward and the vertical velocity of the center of mass increases. The highest upward velocity is reached just before the feet leave the ground. This moment is called takeoff. Here, the estimated center of mass is around 110 centimeters high, and the force drops to zero as the feet leave the ground. During propulsion, movement velocity increases all the way toward takeoff. According to the force-velocity relationship, during concentric muscle action, the faster the muscle shortens, the less force it can produce. Power can still be high because power depends on both force and velocity. If we look carefully at the force signal during propulsion, we can see a second local peak before takeoff. We will return to that in a moment. Flight and landing. Once the feet leave the ground, the flight phase begins. During flight, the person no longer applies force to the force plates, so the force signal drops to zero. The body continues moving upward, but gravity slows the motion throughout the flight phase. At the highest point of the jump, the center of mass has risen to around 163 centimeters. At that moment, the vertical velocity of the center of mass is briefly zero. After the highest point, the body begins accelerating downward until landing. During landing, the force signal rises rapidly because the body is moving downward and the movement must be stopped in a short time. The landing force peak can be larger than the force peak during takeoff. After landing, the person stabilizes and the force signal gradually returns toward body weight. Why are there two force peaks? During the propulsive phase, we can identify two local force peaks. This next part cannot be explained from the force plates alone. To understand it better, we also use 3D motion analysis. With motion analysis, we can estimate joint moments and examine how the hip, knee, and ankle contribute during the jump. Here, the force curve shows the vertical ground reaction force of the whole body. On the right, we see synchronized joint moment curves for the hip, knee, and ankle extensors. These curves help us understand how different lower limb muscle groups work against the external forces during the jump. The light green and dark green curves represent the left and right sides. The hip extension moment stays relatively steady through the jump. In this example, the hip reaches a peak of about 2.5 Newton meters per kilogram per side, and the peak occurs near the bottom of the counter movement. The knee extension moment also has a clear peak. Of these three joints, the knee has the largest peak moment, around 3.5 Newton meters per kilogram per side. The highest knee moment also occurs near the bottom of the counter movement. The ankle moment is smaller, around 1.3 Newton meters per kilogram per side. However, the timing is different. The ankle moment peaks later, closer to takeoff. Now, let's connect these joint moments to the force curve. The first major force peak occurs near the transition from braking to propulsion. At this moment, the hip extension moment is high, and especially the knee extension moment reaches its peak. This suggests that the braking and reversal of the downward movement are mainly produced by the hip and knee extensors. As the propulsive phase continues, the body accelerates upward. Movement velocity increases, and the ability to produce high concentric force decreases. This is one reason why the total ground reaction force starts to fall after the first peak. If we pause at the valley between the two force peaks, the main explanation is that the knee extension moment has dropped substantially. The quadriceps may still be working in a good position, but the knee is extending quickly. At higher shortening velocities, concentric force production is reduced, even though power output may still be high. The hip moment remains relatively high because the hip extensors still support and accelerate the trunk. The arm swing also contributes here. As the arms move forward and upward, the trunk and lower limbs must coordinate against that motion. Then, as we move toward the second force peak, we can see that it lines up more closely with the peak ankle extension moment. At this point, the ankle plantar flexors are contributing strongly during late propulsion. The arms have also reached high upward velocity, and their motion affects the whole body force pattern. Together, ankle extension, arm swing, and whole body coordination create the second local rise in the force curve. So the second peak should not be interpreted as the force of one single muscle group. The force plate measures the total vertical force of the whole body. In this example, the second peak is best understood as a combination of late propulsive ankle contribution, arm swing timing, and coordinated extension of the whole body. This analysis is also highly individual. There is no universal optimal force curve for every jump. Body mass, body proportions, muscle attachment points, neuromuscular coordination, tendon stiffness, strength, and technique all affect the amount, timing, and distribution of force production. Different CMJ examples. Let's now look briefly at a few different CMJ performances. Here is another two-leg CMJ. Even though the exact force curve is slightly different, we can identify the same main events: standing, unloading, braking, propulsion, flight, and landing. In this example, the propulsive phase can again be divided into an early part and a late part. The exact shape of the force curve depends on how the person coordinates the hip, knee, ankle, trunk, and arm swing. Now let's look at a loaded CMJN. In this example, the person performs the jump with an additional 60 kilogram load. During the weighing phase, the force plates show that the total system load is now about 140 kilograms. This includes both the body mass and the external load. The phases are still the same, but they naturally take longer because the load is heavier. The force time curve changes, and the movement is slower. At peak force, we can also see a noticeable asymmetry between the left and right force plates. The left side is loaded more than the right side. In this case, the asymmetry appears to be related to the bar position. The bar is not perfectly balanced on the back, and this changes how the load is distributed between the legs. This is also visible in the joint loading. The left knee shows around 30% greater loading than the right knee. This is an important practical point. When external equipment is used, setup matters. An uneven bar position can create asymmetry that reflects the test setup, not necessarily the athlete's true capacity. Finally, let's look at a single leg CMJ. A single leg CMJ can be useful when we want to make side-to-side differences more visible. However, the movement strategy is different from a two-leg jump. In a single leg jump, it is usually not useful to drop into a very deep counter movement, because rising from that position is harder to perform explosively on one leg. Compared with a two-leg jump, the joint loading profile also changes. In this example, the hip and knee extension moments again peak near the deepest point of the counter movement. The hip moment remains at roughly the same level as in the two-leg jump, but the peak knee extension moment is about 30% lower. Part of the force production is now used for balance and movement control, not only for vertical propulsion. The peak force on the force plate does not occur at the deepest point of the counter movement. Instead, it occurs closer to the peak ankle extension moment. In this single leg example, the peak ankle moment is also about 50% higher than in the two-leg jump. This shows how single leg jumping can shift the demand toward balance control and ankle contribution. Final takeaway: force plates tell us what happens against the ground. Video and motion analysis help us understand how the body produced that force. Together, they turn a simple jump test into a biomechanical analysis of movement strategy. Thanks for watching.